In this demonstration, we'll see how 3DC design is a best practice for DC and warehouse design. The 3DC design approach offers advantages over the traditional approach. Inventory, demand, and workflows, instead of being analyzed as separate factors, are integrated into a single iterative process. Instead of using separate, disconnected systems for process analysis and drawing, one system integrates these functions. Design scenarios, limited to one or two possible layouts, are instead defined by all combinations of design factors. The traditional solution, though likely functional, is a separated collection consisting of a space plan, a labor plan, and an equipment plan, while the 3DC design solutions are integrated in order to understand the trade-offs between space, labor, and equipment. The risk of traditional design leaves customers wondering whether a better way was overlooked, but satisfaction is complete when the customer understands that all solutions have been analyzed and costed. On the left, the result of a traditional design approach shows the cost impact of two possible designs. Using the 3DC design toolset generates thousands of scenarios, allowing customers to understand the full breadth of possible design solutions. The design environment involves trade-offs between the three key design factors of space, labor, and equipment. For example, a narrow aisle facility can save space but cause slower travel. Automated material handling equipment might improve labor productivity, but with a higher capital investment required. 3DC design analyzes client data to generate the best design solution. How does it work? The design toolset consists of three software modules, one for storage, one for travel, and one for MHE, or material handling equipment. Inventory data is analyzed in order to wrap the right storage solution around the inventory. Examples include bulk floor storage, select rack, and deep storage solutions like drive-in rack or pallet flow rails. The optimal storage media includes information about location, depth, and height. That information, combined with the client demand profile, allows the system to generate multiple aisle and cross-aisle scenarios. These travel environments each have different distances, which become a key input into the MHE module. Workflow type, frequency, and capacity requirements over the various distances determine the best equipment for the fleet. It is the final analysis of optimal storage media, all possible travel scenarios, each with a best fleet of material handling equipment, that reveals the client's best design solution. Inventory data usually consists of storage and demand information by item number. Data analysis determines the relationship between storage requirement and the rate at which inventory is picked and replenished. In the storage module, the data is captured in terms of key modeling information like the number of pick faces and the requirements for the use of deep storage. Additional data related to the total locations required, location size, and other information allows the system to generate actionable statistics. Location count by storage media can be used for the racking bid process. Floor aisle locations provide key intelligence so that drawings show the correct relationship between aisles and total locations. And storage media aisle length provides the first data point for creating travel simulation in the travel module. The travel module manages models and data from this control page. Models are managed in the pane at the left. We might have different models for different buildings, or when significant changes are made to an existing building. Building specifications are managed in the central pane. Physical dimensions include the total aisle length, aisle width, cross-aisle width, slot dimensions, and overall floor space length and width. ABC location is used to set the starting point for warehouse slotting. To the right, scenario ranges are set up. The travel module will consider multiple aisle and cross-aisle counts for the same building specifications. The results pane shows the outcome of model simulation. Here we find the aisle and cross-aisle configurations for each scenario. The scenarios each have an average travel distance. To the right, the results pane shows the square feet required for each layout scenario. Data in 3DC Travel can be exported to Microsoft Excel for further analysis and reporting. After the model has been generated, the layout area provides a graphical interface for understanding the results. A baseline layout visualizes the starting point for modeling. This facility is 144,000 square feet with 22 aisles of single select rack and 2 cross aisles, one at the front and one at the back of the storage area. The depot or travel start point is in the southwest corner. Often, a layout must accommodate areas that are not available for storage or travel. An office or value-add area in the building must be excluded from the design. 3DC allows for design and scenario modeling while excluding these areas. Once a baseline facility is established, we explore possible improvements. A data analysis of inventory allows slotting logic to be modeled in 3DC. Slotting here is designated to begin at the south wall. Slotting reduces travel by 23%. Modeling a cross aisle allows us to see the trade-off between travel and square feet. In the example, the combination of slotting and a central cross aisle reduced travel by 870 feet, or 36% from the baseline. At the same time, the central cross aisle adds 8,718 square feet, a 6% increase over the baseline. The travel distance becomes a key input in evaluating layouts in the MHE module. Here the distance of 1,502 feet will be picked up in the material handling analysis to come. Meanwhile, the travel module can be used to map complex facilities. This layout shows bulk locations or other deep storage media. Locations can be set to any dimension in order to correctly model and simulate workflows. Here, multiple aisle widths and storage configurations are modeled. Simulation results are more accurate when the modeled layout reflects the actual operation. Any layout can be exported to AutoCAD for viewing and plotting. Here you see the layout as viewed in AutoCAD. Once in AutoCAD, the design can be finished and printed as needed. The next question becomes, what will it cost when we apply distances to the facility volume? We turn to the MHE module to continue the analysis. First, we set up a model. We'll call this model Assessment. Then we'll type a description for what we expect the model to do. We're going to assess opportunities for a fleet of sit-down counterbalance units. We start by defining the current fleet. In this example, the facility has a fleet of 30 units, all of which are counterbalanced 5,000-pound units that run on liquid propane. Next, we enter the operational processes and material flow nodes. Operational processes are the moves performed by the equipment. We have processes for unloading, put away, picking, and loading. We further split put away and picking into horizontal and vertical processes in order to allow the system to consider multiple equipment types. Material flow nodes are the points in the facility where processes start and stop. Here we use the nodes of truck, dock, storage area, and storage rack. Together, processes and nodes are used to describe the material flows. The specification area is used to constrain the solution. We use an expert system, and specifications activate rules in the expert system. For example, 2 of our processes require the current or future equipment have the capability of vertical travel. So here we set rules for the put-away vertical process to allow only for equipment that can travel vertically and attain the height required. At this point, we are ready to define the workflows. For each process, we define a from-to pair indicating where the process starts and stops. Then, we enter data that will allow the system to calculate work volume. Pick time and place time show the time to perform one task. The trips per day and distance describe the work of volume and travel required. The system automatically generates the best theoretical piece of equipment to perform each process. The user can choose to accept the system solution or replace the system solution with any other type of equipment in the library. Reports help the user compare equipment. This report shows the current equipment and then all other equipment types in descending order of cost effectiveness. In our example, the user chooses to override the system solution of a triple pallet jack and instead selects a rider pallet jack for unloading and loading. System reports can be viewed on the screen or exported to Excel. Here, the results have been exported and used to build a chart in Excel to visually compare current cost to future cost. Significant labor savings result from using higher capacity equipment for the horizontal processes related to put away and pick. At the same time, since less equipment is required in the new fleet, there are additional savings in depreciation expense. The analysis is complete. 30 counterbalance units with a total cost to operate of $664,000 per year have been replaced by a fleet of 20 units that combines rider pallet jacks with counterbalance equipment. The total cost saving is 48%. 3DC design uses simulation, expert system, and combinatorial analysis to achieve best practice for DC and warehouse design.